Yeah, hello guys. Yeah, in this tutorial we are going to discuss the problem number 199, and the title of the question is binary tree right side view. It means usually there is a binary tree and you are looking from the right side, and when you are looking from the right side due to the obstacle of the right node you are actually don't have a viewpoint to the left node. It means it is actually overlapping, so you are covering the left node and you are making the choice by the right node. It's not about choice, you just need to add the nodes that you're actually seeing when you're seeing from the right side. Means I'll show you the example as they gave in the lead code. That would be more beneficial. This is the binary tree, right? So when you lean from the right side, assume that in kind of 3D animation, then the right node covers the left node, so you only have view of the right nodes. Then what are you seeing? Those nodes you need to actually put them in a list and return them. So that's what they want us to do. There isn't anything. And if you see this example, when you see from the right, you're gonna always have the root, and this is being overlapped by this right node, so you got the tree. But see here, this tree doesn't have any child of right and left pointers, so it doesn't actually stop you from seeing this one, because the you're seeing from the right side part, right? So there is nothing, so you can actually see transparently. So that's what this example shows you. So let's go into the code and understand what's the approach and solve the question. Yeah, so let me take my pencil. Yeah, so they'll just give you a root node one, and this is a DFS approach. I'm just telling you now, only if root value is equals to null, you'll just return. When this is the case, when 4 is actually null, you'll return. That's it. And if level value equals to result dot size, level value is nothing but at every level you'll just have an option of adding only one node, because assume that even if you have here another node, you're gonna add this one. Suppose assume that this value is 4. You think you're gonna add this node? Never. You can't never add this one, because this is the left node of these both. And sorry, this is the left node of this node 4. So, let's keep this node as 9, and this node was actually being covered by this node, so we won't actually get the view of node 9, and we'll just use the node 4 only. So that is the same reason actually applies for here also. Even this is right or left, it doesn't actually matter, they're actually on the same level. So we will discard this node. If you see this node, this is the right node and this is the left node, and they're on the same level, so right node is actually dominating and not making us to see this left node, so we don't do that. But root node, it is actually single node, and if you see from the right side you will get the view. So you will this add this one, this one, because you are seeing from the right side, right? So we just need to do add them in the list, resultant list. And at every level you can add up to one node only, you can't get more than one. Try as you wish. Example, you will just get only one node, so those all nodes you need to return. So that is the reason here if you see we are just adding level plus one. Means level is nothing but the number of nodes, and in this level what we're doing, that one only, that doesn't anything like that. So if level value is equals to result dot size, what is level and result dot size? Level is nothing but we are passing 0, and here we're using that. Wait a minute, yeah. And what is result? Result is nothing but a level here, and result is a list, and which is of a type integer. So result dot size is actually 0, and level value is also 0. So 0 value is equals to 0. That is true. It means what we need to do, result dot add node dot value. We can add the node dot value, and currently our list value is actually 1. And then what we need to do, ds of root node dot left comma result comma level plus 1. Level value is currently being 1, and result dot size also being 1, because we actually being added a single element into the list, so it is being the size of 1. And level value is being incremented here, will come from top, and we'll do the same thing, is node value equals to null. We are going towards right because we need to prefer the right one only. That's what they intended us to do. You need to do from the right side view. So we'll traverse the right left way, and before doing that you will check this case, if left value is equals to result dot size. Is that true? Yes, that's true. So then add result dot add node dot value. Result dot add node dot value means, here previously we done node dot right, we are pointing at 3, and node dot value is actually 3, so you'll add the 3 here. And then you're actually doing a, and we done that, and we are actually calling a recursive call, and where left plus 1, left where, sorry, left, it's not left, it's actually level, and level became 2 now. So you're coming from the top, and what you're doing is you're doing the same thing, node value equals to null. Currently our root value is equals to 4, and it is not equals to null. So level equals to result dot size. Is 2 equals to 2? Yes, that's true, because level value actually being 2. I haven't noted that, but I do remember in my mind. If you are actually focusing on that, it doesn't matter to you. So level is equals to result dot size. Yes, that's true. Result dot add node dot value, which is actually 4 in this case. And we're done that adding, and result dot dfs of root dot node dot right, which is actually pointing towards null, and we're pointing towards null now, and comma result comma level plus 1 equals to 3, level equals to 3, and we're pointing at null, and we're coming from top, is node value equals to null. Yeah, that's true. Return. So return, we don't return anything, we just come to our parent node, and we're at 4. And when we are at 4, we'll do this call, node dot left comma result comma level plus 1, level equals to 2 plus 1 equals to 3. Yeah, we'll do that, and we'll just get the same thing. We'll just return, and we'll point to the 4 again here only, and then we'll return to this one, and this will actually call the this for this node right is actually completed, and we need to call left at the last line, and we'll do that, and we'll get return of nothing, just to be same way. And for this node right is completed, so you will call left, and again right will be called, but you don't add them, because remember, here it was never going to be result dot size value equals to value, because actually result dot size doesn't actually decrease, but the level size may decrease, because it's about the matter of stack frames. At every stack frame the values being changed, but not the result dot size, because that doesn't being const, that does not actually be a constant, so it doesn't match. So we don't add anything, and we'll just return this result at the end of the main function, where we actually be called the dfs. After calling that, we actually return the result. That's what they wanted us to do, and we actually see it. We actually watch what's the right view of the binary tree. Yeah, that's it. Thank you.